Hi, I'm Hans. Today I'd like to tell you a little bit about my research. In doing so, I'd like to reach as large of an audience as possible. Whether your background is in an applied field such as signal processing, information systems, or machine learning, or if you're from a pure math background such as lattice theory, sheaf theory, or applied topology, or even applied category theory, this video is for you. Let's get started. I begin with a simple question. What is a Laplacian? Everyone is familiar with the Laplacian from multivariable calculus. This Laplacian is found in the heat equation, which models the diffusion of heat across a surface. Maybe you are familiar with other Laplacians, like the Hodge Laplacian of a chain complex, which specializes to the combinatorial graph Laplacian. The graph Laplacian is an operator on the space of one-dimensional signals over a graph. Initially, some components of the signal are red, while others are yellow. As time passes, nodes average their components of the graph signal with the components of their neighbors. Asymptotically, the signal on the graph becomes locally constant, in orange hue. The nodes reach a consensus on what their final signal will be. In the case of the graph Laplacian, it is the average of the initial signals over all of the nodes. The graph Laplacian is very useful for processing scalar or vector-valued signals over graphs. Suppose you want to process other types of data, such as logical, hierarchical, or relational data. There is a Laplacian for that, which I call the Tarski Laplacian, named after a Polish mathematician, Alfred Tarski. The Tarski Laplacian is an algebraic and combinatorial network diffusion model. To understand the Tarski Laplacian, we will need a little lattice theory and the notion of a network sheaf. A lattice is a partially ordered set such that any two elements has a least upper bound, called a join, and a greatest lower bound, called a meet. We can draw a lattice with a Hasse diagram. Two elements are connected in our Hasse diagram with an edge if one is less than the other and there is no element in between them. We can visualize joins and meets in our Hasse diagrams. Galois connections are particularly nice maps relating a pair of lattices. An antitone Galois connection is a pair of order reversing maps called left and right adjoints between lattices K and L, such that f left of x composed with f right is greater than or equal to x, and f right of y composed with f left is greater than or equal to y. Concept lattices are an interesting class of lattices constructed from a binary relation over two sets x and y, and a natural antitone Galois connection between their power sets. Concept lattices depict a hierarchy of subsets of objects that uniquely share a subset of attributes in common. They are useful in many areas, for example, in data mining. Sheaves are a tool from algebraic geometry for assigning arbitrary types of data to, say, a network, and encoding constraint between the data defined in a local way. How exactly are constraints encoded? They are encoded in restriction maps between objects over nodes and their incident objects over edges. A constraint is satisfied if the components of the signal over the nodes, when pushed to an edge with a restriction map, agree over that edge. Signals that satisfy all local constraints are called sections. Sections are an instance of a ubiquitous construction in category theory called a limit. One example of a sheaf is a constant sheaf, which stores the same object, pick your favorite, over each node and edge. Restriction maps are the identity map. It is easy to see that sections of the constant sheaf are locally constant signals. Remind you of the graph Laplacian? It should. The Tarski Laplacian is an operator on the set of lattice-valued signals over a graph. Technically, it is defined over a sheaf of lattices. Like the graph Laplacian, the Tarski Laplacian propagates local components of a graph signal to the entire graph in such a way that respects local constraints. Instead of taking averages of signals supported in a neighborhood of a node in a graph, the Tarski Laplacian makes use of the join and meet operations in a lattice, as well as the Galois connections that encode constraints. Signals over nodes of a network are pushed forward to their incident edges, with the left adjoints. Joins are taken. Then, signals over edges are pulled back with right adjoints. Finally, meets are taken. This process can be iterated in the same way that the graph Laplacian can be applied over and over to process signals at different scales. Eventually, the graph Laplacian converges to a constant signal. What about the Tarski Laplacian? The fixed point theorem relates the suffix points of the Tarski Laplacian with the set of sections over a sheaf of lattices. They are equal. This is a beautiful theorem for a few reasons. One is that the sections can be computed by iterating the Tarski Laplacian. Another is that the set of all sections, these are consistent lattice-valued graph signals, is a lattice in its own right. This is a consequence of the Tarski fixed point theorem. Currently, I am working in a few application domains where I think the Tarski Laplacian will shed light on various what I would broadly call information diffusion problems. I will say a little bit about a few directions my work is heading. I am developing a new paradigm for graph neural networks based on lattice theory. A graph neural network is a deep learning architecture in which input signals are supported on a network, rather than on an image or a time series that we see often in traditional deep learning. However, sometimes in graph neural networks, input feature vectors are endowed with a partial order over the coordinates. We are working on processing this kind of information with the Tarski Laplacian in order to define new graph neural network architectures. Manjarda et al. Introduced a theory of consensus for lattices of social choice functions. These functions take a set of choices, for example, restaurants you want to eat at, and narrow them down to one or a few choices. We are working on extending this work to understand not only lattices of preference relations, but lattices of meta-preferences, preferences about preferences. The Tarski Laplacian comes into play when one is aggregating their preference relations by sharing them with their neighbors in a social network. In certain multi-robotic systems, robots need to aggregate information they gather to other robots in an ad hoc wireless network. The kinds of information they need to aggregate is not limited to measurements that are Euclidean, but also semantic information. For example, robots can learn and propagate to their neighbors complex logical dependencies between the environment and other robots in the system. The Tarski Laplacian offers a diffusion model for these sorts of semantic problems. I hope you've enjoyed learning a little bit about my research. Let's recap. We began with a simple question. What is a Laplacian? And specifically, how one can generalize the graph Laplacian to handle lattice-valued data, thereby paving the way for the Tarski Laplacian, a distant cousin of the graph Laplacian. I presented a lattice-theoretic fixed-point theorem that mimics the property of the graph Laplacian that all initial conditions lead to locally constant graph signals. I then shared some directions my research is heading. If you liked my content, please give this video a like. You can find my information, Twitter handle, publications, and occasional blog posts on my webpage, hansreis.com. Please feel free to reach out if you have any comments or questions or would just like to connect. I'm currently on the job market. Thank you.